Hello, welcome to my today's presentation, which is all about full bridge converter verification. My name is Markus Sonst. I'm an application engineer at Rohde & Schwarz and responsible for power management topics. What is the content of today? Well, we will start with different power architectures. Then we will continue with the principle of operation of a full bridge converter to get you on track. Then a very important point of a full bridge converter design is the isolation and the impact of the system design. Then we will have some typical measurements, which is also quite important in this converter type. And finally, we will end the presentation with a conclusion. So the big question is, why do we use, or why did I choose the full bridge converter design for today's presentation? Well, it's very often and frequently used in telecom and server applications, so really a common topology. It provides galvanic isolation, and that is exactly the topic what I wanted to cover today. It also transfers higher power, and it provides also a high degree of complexity. And therefore, of course, we need also the right measurement tools to have the capability to solve this complexity, or simplify it, basically. So now let's start with the power architectures. This is one solution what we can have. This is a so-called distributed power architecture, and it consists of an AC-DC converter always at the front end. Of course, we need to convert AC to DC to create this DC system bus. That is typically also a backup with a battery in case the AC power fails. And this DC system bus supplies a multiple DC-DC converter, where we have basically an isolation barrier in each DC-DC converter. And then we have here at the output the different voltages, where we supply basically the digital circuits. The problem what we have here is basically that the new technology in digital circuits require much more lower voltages and higher currents. And therefore, we need to change this power architecture. So problem here is really, it's not compact, it's less efficient, and we have really also a high system cost due to this isolation barrier. And this is what we want to solve basically in another power architecture. And the next architecture we will have here in this presentation is intermediate bus architecture, IBC. And in this architecture, the front is basically the same. So AC-DC power supply and a battery backup, but we have only one centralized intermediate bus converter here in the middle of the system or in the architecture. And there is also the isolation barrier provided. And from this intermediate bus converter, we have an IBC bus, which ranges from 5 to 12 volt basically. And that is basically providing the point of load converter, where we have multiple converters to generate these lower voltages for the complex digital circuits we have nowadays. The benefit here is really we have only one isolation barrier in one converter, which simplifies the system. And we have only a point of load converter, which is a non-isolated type here at this point. And this gives us also the possibility to relax basically the regulation requirements for this intermediate bus converter, because we have a two-stage system, the intermediate bus converter, and then that is followed by the post regulator. Furthermore, don't forget that we need also a power-up sequence for these new digital circuits or processors. And that can be also easily included or attached to that system. So this here, in this waveform here, should be common to you, that we have a certain power-up sequence for the digital processors. The question is now, well, now we have defined this intermediate bus converter. What kind of converter could be used for that purpose here? And I want to give you some examples. And this is one, the so-called push-pull converter, where we have basically, of course, a transformer as a central part. And then we have two low side switches here. and a rectifier at the output with two diodes. And yeah, that's it actually with the structure. And the benefit or advantages here in this converter are basically that we utilize the transformer core quite well compared to a forward converter, for example, because it's a double-ended topology. And we are driving the core basically in two quadrants. Furthermore, we have two low-side switches. That means we don't need a high-side driver, very simple to drive, and low EMI emission due to this symmetric structure. Of course, some disadvantages come along with this converter type, and one is, okay, it's a bit limited in power. So up to 200 watt is its maximum. But another problem, or a bigger problem, is that we need to select the MOSFETs in a way that we can resist 2 times the input voltage, which makes it in some cases, applications, a bit inefficient. And last but not least, the transformer saturation may occur when you have this common flux walking in the transformer core. But okay, this is usually covered by the controller. And yeah, some applications are typical applications are high-side driver applications in automotive where they need really low EMI. The next converter type we could use for this intermediate bus converter is the so-called half-bridge converter. Output side, secondary side is pretty much the same. At the input we have 2 capacitors and a midpoint and 2 MOSFETs in series. And they create basically the bridge leg where we have the primary winding connected. The advantage here are that we can provide or convert higher power levels. We have less voltage stress compared to the previous converter. The transformer design is simplified because we have only a single primary winding and not a midpoint here at this point. So it's easier to design. And yeah, we also utilize the core quite well. The disadvantages are that we need to drive the high-side driver, high-side MOSFET. And yeah, we need also a supply for that. And that is sometimes not very easy. So you need actually a high-side supply on top of the switch node. And the cross conduction may occur, so you can have a short through when you don't limit the dead time. Yeah, last but not least, the main topic of today's presentation, the full bridge converter design. So another half bridge leg basically is added, and in between the primary winding. So we could get rid of the second capacitor here at the input, which is nice. One benefit, we can actually transfer higher power levels with this converter design. We have the best efficiency and, yeah, as I said, the single input capacitor. The high-side driver problem is here basically the same. So we have it now 2 times, but okay, when you can solve it once, it's not a big deal to do it a second time. But of course, this system is really costly because we have thrown a lot of silicon into the circuit, and the complexity also is increasing. Even that is not the final version I would like to discuss today. So when you have a look on the secondary side here, we have here these standardized diodes used, which of course during conduction, it's not the best way to have a very efficient system. And one solution could be a Schottky diode, but I would go for the switching types of synchronization. So a synchronous rectifier is the keyword here. And yeah, then we have really the best efficiency, but of course, the highest complexity and also, yeah, more cost introduced. But this is exactly what we want to cover today, this full bridge converter design, including the synchronous rectification. Before we do that, we need to go into the principle of operation because a bit of background is needed that we can later on cover the challenges and how we can solve that with our measurement principles. So, converter operation. Converter operation can actually be divided into 4 parts, 2 energy transfer cycles and 2 freewheeling cycles. And it doesn't matter where we start, but we start now with the energy transfer cycle 1, the first one. And the question is how to transfer energy from primary to secondary. We need to switch some components in a non-state. And on the primary, we can do that. And we need to switch 2 switches simultaneously in a diagonal way. So then we can have basically this current flow here through the primary winding. And due to that fact, we can actually transfer energy from primary to secondary. That means, or basically at the same time, that means that also on the secondaries, there is something happening. So we have here, in this case, the lower part of the secondary winding used. So we have here also the voltage across the secondary winding. And then the current will flow through the power inductor here and through the load and the output capacitor and back to the winding. And during that time also energy is accumulated in this power inductor here, and that we will use later in the next cycle. This is quite important to remember, that this power inductor stores some energy. Furthermore, you see that the synchronous rectifier switch is also on. It's not really required because we have also the body diode, but of course, as I said, we can reduce the conduction losses. The diagram here on the top right is indicating the switching pattern or switching states, and that's what we will later on basically verify. Okay, so question is now, what can we do next? So we have at the moment 2 switches closed or in on-state, and the only thing what we can do is to open them. So QA here and QD on the primary side we will open. And then what will happen is basically we have a current flow on the secondary side due to the energy stored in this power inductor, and that is pushing the current into the load and the output capacitors and back through the windings, the secondary windings. Also, we have switched on both synchronous switches, bottom one and top one, and that process is completely independent from the primary side. There is something happening also on the primary side, but that is, as I said, independent, and that is caused by this component here I've drawn, and that is the leakage inductance, and there's also energy stored. We cannot avoid it. And that causes also a current flowing in the primary side, so the primary winding, and it flows basically through the body diodes of the QC and QB. So this is a kind of freewheeling process. That's why I called it freewheeling cycle 1. And the next state what we can change is now to switch on again 2 switches simultaneously, and because we did QA and QD before, now we have to switch the other diagonal switches. And that is exactly what will happen in the energy transfer cycle 2. So B and C will be switched on, and that causes the current to flow in the opposite direction, and also the voltage across the primary winding. And that is exactly what we want to have to drive the core in both quadrants. That's quite important. And as I said, the energy cycle transfer 1 is again, we transfer real energy from primary to secondary during this time. So we have again a current flowing in the secondary, on the secondary side, from the caused from the secondary winding, the top one this time. And we are accumulating again energy in this power inductor and pushing the current into the load. And during this time, we have also the synchronous rectifier switched on to reduce the conduction losses. So pretty simple, it's just the opposite direction compared to the cycle 1. And then finally, we have another freewheeling cycle to open the switches. So that's basically this very similar or the same what we had in the freewheeling cycle 1. So current is flowing on the secondary side independently and provided by the power inductor. And yeah, the leakage inductance is causing the current flow on the primary side. And yeah, the corresponding switching pattern we have here in the top diagram now, and then we start again with the energy cycle 1. That's actually all what we have to know about this converter operation, at least on a certain basis. And yeah, that is at least sufficient to understand the challenges here. Because what we will do later on, we will have to verify this switching pattern here, that this is correct. Because when you consider using a digital controller to operate all these switches, it is very important that because you are programming these switching states, that they correlate to each other in a correct manner. And that is exactly what you have to verify later on. One example is when you have here this freewheeling cycle 2, and when you start to enter the energy transfer cycle again, you need to be sure that you have to open the synchronous rectifier 1 and 2 at this point before you start with an energy cycle. There need to be an at that time, for example. And if you don't do that, you have basically a short here when you start to push energy from the primary to the secondary. So these kind of measurements you have to do and to have to ensure that there is some delay in between. Before we go into this measurements section, we need also to understand the isolation topic. As I said, it has really a big impact on the design, on the system design, but not only on the design, also it's relevant for the measurement. And before we go into the details, the definition of isolated and non-isolated, it's not so complicated. So in an isolated system, we have basically 2 circuits separated electrically and galvanically, so that no direct current can flow from the primary to the secondary. This is at least the definition for isolated, and yeah, for non-isolated, it's even more easier. That's just a simple buck converter in this case here. And of course, there can be a direct current from the input to the output. So there is no separation, basically. It's one circuit. Where you can also easily see that in an isolated system, we have here, for example, this ground symbol, which is different from the primary side. And that indicates clearly that it is a different potential and a different circuit. Whereas we have here in the buck converter only one ground symbol. But the more important question is, why do we need converter isolation at all? This is actually what we have to answer, and there are, of course, several reasons for that. And the most important thing is basically we have to fulfill this or follow this safety regulation and standards. Otherwise, you cannot develop your product and bring it to your market. And yeah. And the safety and regulation and standards exist because we want to reduce the risk of the user. And this is possible when you provide isolation in the system. So this is quite important. And there are 2 levels, insulation levels basically. One is the basic insulation level, and the reinforced is just 2 times the basic. And in some cases, for example, in medical applications, you cannot live with one basic insulation level. So you need another one, another layer basically. This is all about safety, so quite important and relevant topic or reason. The other reason to have an isolated system is breaking ground loops. That can also cause a lot of trouble in big systems when you don't separate the different circuits. And that's why the people like to break ground loops. And here we have basically an example where we basically separate a sensitive circuit from a noisy circuit. So the V1 here is let's say the noisy part, and introduce some noise here, because if the circuit is not separated in the ground terminal, you have a common ground resistor here. And even if that is very low, we have some potential here at this point, what you would see also in the sensitive circuit at this point when you measure against ground. So they are basically combined, and this is exactly what you don't want to have, and that is possible when you to avoid when you break ground loops. So quite important as well, but it's a functional reason and not a safety reason. Use cases of converter isolation, well, there are some of them. We have here, at least in the power electronic world, always the problem to provide a small supply on top of a higher voltage potential, and that is exactly for the high side driver required, because we have here this output switch node where we have this up and down and at high voltage potentials. But we also need this supply for this driver here. And that needs to be isolated on a functional isolation level. So this is also one application where where isolation really can help us. The second one, it's quite simple, but it's also possible to have a symmetrical supply for analog circuits, for example, op-amps. Don't forget that when we are talking about isolation systems, we always have to provide a transformer, and this transformer also has a transformer ratio from primary to secondary, and by that we also can basically convert a higher voltage down to a lower voltage, because that is quite important when you really think about high voltages. You cannot do every conversion with duty cycle variation. So this is where the duty cycle is a bit limited, and therefore the transformer helps in addition to convert higher voltages to lower voltages or vice versa. Of course, we have some trade-offs, disadvantages of isolation. One, of course, is the size, because when we are talking about isolated systems, we also need to introduce new components like the optocouplers, auxiliary supply, and isolators. So you have more components typically, and also it adds, therefore, complexity, but not only in the hardware, also in the design process. For example, you have to test the isolation, and even in the production, you have to ensure that the isolation is correct. Of course, transformer losses wouldn't be there when the transformer wouldn't be there. So yeah, it reduces the overall efficiency in the end. And yeah, this is also a fact with what we cannot avoid. The control of a converter is more complex in an isolated system because, yeah, due to this optocoupler, for example, these new components, we need to consider also new characteristics of these components. And the bandwidth, for example, of an optocoupler is limited. That has to be considered in your design, and also the lifetime is a bit limited of optocoupler. And also this needs to be considered during your design. And when we come to measurements, because you want to verify your design, also that is a challenge it's at least more complicated and more complex, because you have to, due to this isolation, you don't need to violate that, or you must not actually violate your isolation barrier, and therefore you need really a good selection of probing. And the key word here is the differential probes. We come to that in a few minutes. Here is now an example of an isolated system design. And what I wanted to show here is basically the large impact on the system design. What we have seen before is only the power stage, so the full bridge and the rectifier, and of course the load capacitors and so on. But we also have additional components now, because yeah, we have a controller here on the secondary side, And we need transfer and receive several information from the circuit. So on the secondary side, it's quite easy. There is no isolation barrier to drive the rectifier. But yeah, to drive the full bridge, the switches, we need actually this information transfer via the insulation barrier, and therefore isolators are used basically. Then we need to sense also information from the primary side back to the secondary side, to the controller, to make a proper or good control. And then finally, there's also the auxiliary supply here, which also need to fulfill the isolation barrier. And that auxiliary supply is required because when we want to start the converter at the beginning, we don't have any energy here or potential at this point where we provide energy to the controller. So we need somehow a circuit to get it in a steady state condition, that converter. And that is where we use this auxiliary supply. Important to mention here is basically that due to these isolators here, for example, you introduce some delays from the controller to the full bridge. And that is what you need to consider when you do your dead time calculation and measurement. You need actually to know how many delay are introduced here by the isolator. And that's why it's so important also to measure these values. Yeah, as I said, auxiliary supplies are required for startup of the controller. That is also part of the measurement section, what we will cover later. Okay, let's start with the switching pattern. I called it switching pattern, and what does it mean? It validates all switching state and their correlations to each other. So what we have seen, this diagram where we have all the switching states and energy cycles, this is exactly what we want to see also on our screen, on our measurement tool, because when we are programming the software, we need to be sure that everything works fine. And the question is, what is the requirement here? Well, we need, of course, for this full bridge converter, at least 6 channels where we need to probe. And 2 of them are here at the gate source voltage at the low side switches. Then we need also, of course, the synchronous rectifier here 2 times the gate source voltage, but also the voltage and current across the primary gives us some information which is interesting. So the minimum what we really need to get a proper switching pattern verification are 6 channels. You might have seen that I also draw here this volt symbol. So we could also introduce here a measurement just to be sure that the diagonal switches here are switching simultaneously. But that is basically, I conclude that basically from the current and voltage here. That's why I used only 6 channels. But that is at least the minimum. So you can imagine it might be difficult to use a 4-channel oscilloscope to get everything on the screen, which is, to get the whole picture, very important. And another, I would say, a requirement is also that we need, for all probing points, differential probes. So we are not allowed or must not connect passive probes with ground leads because of these shunts here. So these red components here, they are the current shunts, measuring the current on the secondary and also on the primary. And when you imagine you connect your ground lead here to this ground potential, you will short that, at this point here, you will short basically your system or your current measurement system. And this is exactly what we don't want. We don't want to have any impact by measuring onto your system. So this is quite sure. And therefore, I really recommend, and it's in my assumption, it's a requirement that we need really differential probing to avoid these kind of problems. Another point is not only the shunt here which matters, it's also not that we want to short basically this ground with this ground here. So when you imagine here, you switch, you connect your passive ground lead here, and here you have basically shorted your system via the oscilloscope. And this is exactly what we don't want, because you must not violate your isolation barrier. And yeah, this is definitely important. Switching pattern essentials, what does it mean? Well, we have seen here we want to verify these switching pattern. We have seen these 5 waveforms in the previous slides. In addition, I also have drawn here the primary winding current, which is important to identify that the transformer, for example, the core is not in saturation. And in addition, I added two additional signals. They are called QD and QB. So there's also the information behind that waveform here of the switches here, which are here in the top of the diagram. But this is measured at the secondary side, and that is directly at the controller. And the reason I did that is basically to be able to measure the delay. So the information is exactly the same here when you compare these two waveforms, but we will have a short delay between the two waveforms. And this is exactly what we want to see later on. So because I had 2 channels basically left, so I added this additional information to gather a lot of information in one shot. So yeah, as I said, a simple correlation according to the pattern. That's why we do this, and it provides us really the whole picture. Delay measurement between primary and secondary isolator, and what else can we do is basically, yeah, we can also measure rise and fall times with this automatic measurement capability of the instrument to identify oscillations, overshoots, undershoots, rise time, fall time, and so on. So once you have this setup, because it takes time to build it up, you can of course activate every function you can get on the oscilloscope and then gather as much as possible of information. And yeah, primary and winding and voltage and current, there as well, oscillation, overshoot, rise time, fall time, and quite important, the current saturation can be covered here. How does it look in practice? We have here the measurement, what I've taken with my system. And what you can see there is basically in the top window, the voltage, the yellow and blue one, the current of the primary winding. And here you can already identify the energy cycle 1, where we have the positive voltage and the positive current, of course. Then that will be followed by the freewheeling cycle, and then again an energy cycle 2 and freewheeling cycle 2. So it's exactly the pattern what we have seen in theory. In the top window, of course, we have the additional channels added. So we have here the synchronous rectifier on this voltage level here, and then of course the primary switching information here on these 2 levels, and here as well. What we else see is basically 2 gates I have defined here, here and here, and that was the reason because I wanted to measure the dead time between the synchronous rectifier switches and the primary switches. And that is basically here shown in this table, including all of the history what you can get with this automatic measurement tool. So quite important, because when you think this is only one measurement at one certain working point of the converter, and you need to, of course, to repeat that at different working points, or different input voltages, different output currents, and so on, whatever you have in your system defined. you need to repeat and double check that the switching pattern, including all delays and oscillations, are correct, or that's what you want to see. The next what we will have is the startup phase. I mentioned that already with this auxiliary supply. And this is one of the most complex requirements or measurement you can have basically of any converter, because this startup sequence is always is a dynamic process where a lot of signals are involved. And sometimes, especially when the system is not starting, it's very difficult to get it running in a proper way. So this is why the startup sequence verification is very important. And yeah, due to this complex converter type, we need here for the channel requirement even more than 6, so 8 channels is the maximum what we use here. And that is because we have the same channels what we have used before in the switching pattern. But in addition, we need also the output voltage and current. And yeah, we need somehow to identify that the system is or has reached its steady state. And therefore, we need also the voltage and current, but also how the voltage and current increases, in which kind of slope and time and so on. Because that is, for sure, you need to program that as well when you have your digital design. How does it look in more detail? So this is the waveform, what you typically see. So you have this input voltage start, and then you have somehow an output voltage current here, which is very often a kind of soft start. So it increases gradually in a certain time, because we don't want to have current overshoots and fast edges and so on. So this is actually what you want to see, and then we eventually end or start the steady state condition. And that's why here it's called soft start. And then we need to cover this section. The problem here is basically that we need to look into details over a very long acquisition, and that is really a challenge in terms of measurement. Because we need, when you want to see the duty cycle, single duty cycles, and the variation of the duty cycle, you need not only a long acquisition, you also need to sample in a good way and in a high rate to get everything visualized correct. So high sampling rate is required, at the same time a long acquisition, and that is already a challenge. And you need, of course, an instrument where we have a lot of memory as well. And then you can use your tools like zoom, cursors, and also track functions to analyze your soft start sequence. And this is exactly what we will have next. So let's have a look into the results here. So again, top window is voltage and current on the transformer winding, primary winding. And the bottom here, we can identify in addition the output voltage, which is really increasing nicely, smooth, and then enters the steady state. The problem here is basically that we have here in the first millisecond, we have here this high current, which is a dark purple waveform. So it's a kind of inrush current where the controller doesn't behave in the best way, I would say. So that has to be optimized, that we get really at least not such a spike here at the beginning and then have a constant current here. But that is kind of is part of the design process. So that's what we have to do. The problem here is basically when you start with a zoom, it's not so easy because you have really a long acquisition, and when you want to see details, it's hard to do. especially when you want to see the PWM information. And therefore, I would recommend to measure the duty cycle by cycle. And then you can define a track function, which shows you the duty cycle variation over a longer time. And this is exactly what I did here in this result. What you see here in this window and the middle right window, these are basically the track functions, and we have both or 2 times a track function because we have the primary switches and we have also the synchronous rectifier switches, and they obviously are behaving differently. So the bottom, the primary switches are starting from low duty cycle, on duty cycle to the steady state in a good and smooth way, I think. But the synchronous rectifier here, they are basically quite fast, and then they are decreasing, and then they enter the steady state condition. So this is, I think, not the best way to be that fast here. Also because the synchronous rectifier are not so important during the startup time. I would even avoid to use them, and then when you're in a steady state, you can switch them on. So that would be my personal view here on that. But this fast edge here could basically be the reason for this voltage, this current inrush, this high current inrush situation. Another interesting fact here with this track function, or it's more a hint, you see that we have here the synchronous rectifier. There's an additional information here, additional signal added here, and that is basically the duty cycle of the synchronous switches. But that is the digital information directly probed at the controller. And I did that because when you see here this window, we have here the orange waveform where the amplitude basically changes over time because we are ramping up the output voltage. And that is, it's possible, but it's not so easy to find reference levels where we basically measure the duty cycle correct. Because typically when you have a reference, you have 10%, 50%, 90%, and that would fail here in this waveform because of the changing amplitude. It would work when you place your 50% here or use absolute values, but that is a kind of, it's a workaround. So I would always recommend to use digital circuits, but because then you can be sure you have a constant amplitude and also no overshoot and undershoot situation, which makes life much easier. Conclusion. So we try to validate or verify complex circuits like a full bridge converter design, but I think that's clear that you really need the right measurement tools for that, because these kind of converters are quite complex, and using a standard instrument, it's really a challenge, and also it's a lot of it's really a time-consuming task. Therefore, our solution, the MX-05 with eight analog channels, can really help you there, at least give you the best support what you can have. Then in addition, you need also keep your focus on using the right differential probes, or just use differential probes, because the passive probes very often fail in isolated designs. And also because of the shunts. And the additional automatic measurement functions we have in our instruments can really make the life easier when you want to measure delay, dead times, and so on, and increase really the efficiency. Also when you want to document your system or your verification process. And that is typically also part of the design. The startup process I would highlight here, because that is one of the most complex things you can have in a converter design. And therefore you need really as much as possible signals be on your screen to get a proper understanding how the system behaves in this dynamic process. That's really quite important. And sometimes also, I didn't have that in my system. A lot of status signals may be involved and give you some additional information. And that also requires some additional channels. And sometimes also only digital circuits, digital channels. But I think the message here is clear. As much as possible of channels are needed. And last but not least, this full bridge converter design was a hard switching type. So relatively simple, because the extended version of this hard switching full bridge type is basically the phase shifted full bridge to have a resonance converter or bring it in a resonance case that you really have high efficiency with high voltages. And then you really have much more states you have to validate, basically. And this is even more complex, and that's why I think it's only, this full bridge hard switching type is just only an intermediate condition. This marks the end of my presentation. I hope that was interesting for you. Please, for further information, visit our webpage. Thank you for your attention. See you next time.